Okay. Oh, here we are. Hey, everybody. We're here, chapter 16, and we're going to be talking about fluids today and for several days, obviously, as we go through our chapter. We've talked about fluids before, and remember that a fluid is any state of matter that can flow. And for us, the three states of matter that can flow are liquids and gases, which we're super familiar with. We're, around them all the time. And then plasmas are the other ones. We're not as familiar with them just because of where they're located, those kinds of things. They do fall into this category. Generally, though, I'll be kind of basing it on liquids and gases. Fluids are very important in the field of fluid mechanics, and this is a branch of physics, obviously, when our physics half of the year that uses, that studies fluids, but also uses some of the properties of fluids as part of machinery or to do work. So one of the first things to know about fluids is that they can, you can measure the pressure of the fluid, and it's a measurement. There's a formula for it right there on the paper that says, let me see, sorry, that says that you have, there's the formula. Sorry, I have a new computer, so I'm trying to figure it out. That basically says that pressure is the amount of force that is acting on a given area. And so the formula is just force divided by area. The units are either newtons per meter squared, or they're also called pascals. That's after the person who figured all that out. And we'll do some calculations on the next page or so. So again, those will be in your book, but we'll go through them in class. But knowing how much pressure is applied can help you again in terms of engineering a structure, kind of figuring out, strength, dimensions, all those kinds of things. So anyway, so that's where we're starting. Okay, so here are the problems. Again, if you would like to work ahead, feel free. We'll do them in class together also. Okay, so fluid pressure. So I said that fluids can exert a pressure. You have always been under pressure. I know you feel like you're sometimes more than others, but you have always been under air pressure. And here at sea level, if we're measuring that in pascals, and we'll measure it in kilopascals, so it's a number that's a little smaller, you have around 101.3 kilopascals of air pressure on you. Right now and all the time. Since you have been born, you have had this air pressure on you because you're here on Earth. There's air surrounding you. You don't feel it because you're used to it. Essentially, you've never not had this pressure on your body, but also you have fluids inside your body, either liquids or gases, mainly air, mainly a gas that is pushing back from the inside. And so they're pushing from either side and they kind of equal out, and then you don't feel anything, you don't feel it. You do some places where you may experience higher outside pressure that you may have done. If you swim down to the deep end of the swimming pool, you can feel the pressure of the water. You may not be aware of it. It may not be that big to you. Your ears may pop. They may have some problems. They may kind of ache a little bit. That's because the pressure isn't equal anymore. You probably also, a lot of you have been in an airplane or you've driven up in the mountains and your ears cause some problems. It's because the air inside stays the same. It's pushing out with the same pressure, but you have less air pushing on you because of where you are in the atmosphere. You're up higher, so it's not 101.3 kilopascals. It's, something like 99 or, whatever it is, depending on how high you are in the atmosphere. So now all of a sudden, your inside pressure is pushing out harder, and that causes your eardrums to makes your ears feel like they want to pop. So here's the deal with this fluid pressure, though, in terms of usefulness, but also just in terms of how it's different. Solids exert pressure, but they can only exert pressure where they're in contact with another object. So right now you're probably sitting in your chair, and you can only exert pressure downward on the chair where you are in contact, or your book is sitting on the table, and so it can only exert pressure downward. Fluids are different. If you have a fluid and you apply a pressure, that pressure actually gets transmitted to all the parts of the fluid. And so your book talks about, like, when you squeeze lotion out of a bottle, you kind of squeeze right in the middle, and it doesn't just, like, the fluid then gets pushed out, the opening gets pushed out the little cap. If I took a similar shape, like a brick, a solid, and I squeezed it, nothing happens. Those particles are so close together, there's no real room for them to move or, kind of try and get out of the way. Fluids have some space, and so as they are pushed, right where you're squeezing the bottle of lotion, they push other things too, because they can move through that. This whole process, this is called Pascal's principle, the guy that pressure is the unit is from, and it is one of the key components of some of that machinery I was talking about earlier that can help us use some of these fluid properties to do work. Okay, so here's another thing that fluids can do, is they can show the buoyancy of an object. So you know this, that some things float and some things don't, and that depends on the buoyancy of the object, and it also depends on the buoyant force. And the buoyant force is an upward force, so from the underneath of an object, that's caused by the displacement of a fluid. And so this keeps things floating. So when you put something down into a fluid, down into water, like a boat down in water, the water pushes back up on the water molecules from underneath as the boat is pushing down. So the boat pushes down, the water pushes up. And as long as that buoyant force is stronger, is greater than the weight of the boat, or equivalent to the weight of the boat, then the boat will float. And you can do different things to help with that. The shape, obviously, of the boat is has something to do with it, just kind of the flatness of the boat. But also boats typically are hollow, and so there's lots of air inside, which helps the water because the weight is not as heavy. So anyway, so you can have this buoyancy. So that's one of the things that we can look at to determine, okay, will something float or not? So now Archimedes, on the other hand, not on the other hand, but he basically discovered that you can kind of figure out what the buoyant force is. So remember, he was a Greek guy, he's into math and science, like a lot of them were, and he noticed that the amount of water that was displaced by an object that gets put into water, that will, like, sink down into the water, he said that he noticed the water level rising, and he said that the weight of that object is equal to the buoyancy force, or the buoyant force that's acting on that water. And so we can use Archimedes' principle to determine, okay, will an object sink or float? So if the buoyant force is greater than the weight of the object will float. And so, like in our little picture down there, that middle thing, like it looks like a little block of wood, the buoyancy force is greater than the weight of the object, so the object's going to float. If the buoyancy force is less than the weight of the object will sink. So that block of, looks like metal, sinks down to the bottom, and notice how the water is displaced. And so that amount of water is the volume of the object, but also the weight can help us of the object determine it, the buoyancy force that's needed. Okay, so another way that we can determine buoyancy is if you know the density of an object, which again, so many of these things you guys know just kind of from living your life. You may not think of it in these terms, but it works this way. So if you know the density of the fluid that you're putting the object into, you can determine, even before you do it, will this object sink or float? So water's density is 1. This is a nice, easy number to remember. Any object that has a density less than 1 will float because it's less dense than water. Any object that has a density greater than 1 will sink because it is more dense than water. So lead sinks because its density is 11.3. Pine, like a piece of wood, floats because its density is 0.5. And this can refer to liquids floating on other liquids, like oil floats on on water, partly because chemically they don't mix, but it floats because it is less dense than water. Air, air can have different levels to it, or in terms of density. So we talk about, I don't know if you guys have heard, hot air rises, smoke rises, like they tell you, like if your house is on fire, to crawl to get low, because the warmer air rises because it's less dense. The good air, somewhat is down lower. And so so it doesn't just have to be like a solid being put into a liquid. It can be any combination. And again, like I said, a lot of this is kind of natural, intuitive to you, but this is what it's based on. Okay. All right. So neutral buoyancy is what you see when you have an object that doesn't sink or float. It just kind of sits right in the middle of the other fluid. This happens when the densities of the two fluids, whatever they may be, are the same. Fish do this. They maintain neutral buoyancy in water so that they are at a certain depth all the time. Fish have a thing called an air bladder or swim bladder that they basically use to kind of raise or lower themselves in the water wherever they need to be. Scuba divers, I'm not an experienced scuba diver. I'm not a scuba diver at all. Have kind of similar things, kind of the vests that they can wear that they can release air from so that they'll sink, or use their air tanks to fill back up so they'll rise. So it's again kind of a situation that you can kind of adjust depending on who you are. And then I kind of touched on this already. I don't know, I have it here again, but remember that buoyancy is, and densities and all those different things don't just have to be a solid in a liquid. You can have all kinds of different combinations. All right. Okay. Okay, so another property of fluids is viscosity, which we talked about in the last chapter because it was one of the thermometric properties. Remember, the viscosity of liquids will change if you heat them up. So remember, they flow better. Like honey flows better if it's warm. Remember, viscosity is a measurement of a fluid's resistance to flowing. So basically, how hard is it to pour this fluid? If it's high viscosity, it doesn't flow easily. So honey is a good example of something that has high viscosity. Low viscosity are things like water that just pour right out. Viscosity is actually due to friction between the particles in a fluid. And so, for whatever reason, if the structure of the particles, the molecules that make up the fluid aren't, they kind of rub each other the wrong way, that's friction. And so they just have a harder time flowing. And so more friction, more viscosity, vice versa. And so, so viscosity again is a big thing. And we'll talk about it more in class, but viscosity, a lot of times you might hear it in terms of like motor oil. You'll hear commercials like high viscosity motor oil. You don't want your motor oil to be real thin. You want it to be able to coat and lubricate the parts of your engine and that kind of thing. And so it basically, kind of stands up to the heat and, is pretty thick. And so that's kind of the good part of some things that are high viscosity. Okay, so gas laws. We've kind of touched on the gas laws a little bit. But they are laws and they have a mathematical basis that basically deal with how the conditions around a gas can change it. And mainly we deal with pressure and volume and temperature. So first, real quick, gas pressure is determined by the number of particles in in a certain container in a certain area. And so it's like blowing up a balloon. If I breathe into it more, then I am increasing the gas pressure because I'm increasing the number of particles. Gas volume, on the other hand, typically is determined by the size of the container. Because remember, gases expand to fill the container. And so if you have a larger container, we'd call that the volume because that's what your gas will fill up. But it also is you need to take into account the pressure because the gas molecules are also pushing on that container. So again, with the balloon, I can change the size by changing the volume or by changing the amount of particles, and then I can also throw temperature in there, which is what all these gas laws kind of deal with. Okay, so we have Boyle's law. So Robert Boyle, the 1600s, he said that the pressure of a gas is inversely proportional to its volume. So that's kind of the main part. So that means if one goes up, if pressure goes up, then volume will go down. If I am putting more pressure on a gas, I can make it smaller, or vice versa. But you have to remember that the amount of gas and the number of particles stays constant and the temperature stays constant because both of those things can change the other two variables, the pressure and volume. So down at the bottom there is the formula that we'll use. If I can get my little pen to work. Oh, hang on. Like I said, new computer. I'm still trying to figure it out. Oh, so here's the formula. Whoops. And so we will do some examples with that. It's again going to be algebra type stuff. So don't be too worried. Okay, so here is a Boyle's Law problem. We'll go through it in class together, but again, check it out in the book. Work ahead. It will help you out a little bit, but we'll do it in class too. Okay, so then we have Charles' law, Jacques Charles. So late 17th century, he said that the volume of a sample of gas at constant pressure, so basically, not worried about pressure in this one, is directly proportional to its temperature. If something is directly proportional, that means that if one variable goes up, the other variable goes up too. So they're both going up same time. And so if I increase the temperature, I will automatically increase the volume. If I can increase the volume, the temperature theoretically will also go up because the molecules have more space. They can build up more speed. Remember, the speed is temperature in terms of molecules. One thing to note is that when we do these problems, the temperature always needs to be in Kelvin, which typically they'll be given to you in Celsius, so you'll add 273 to get to the Kelvin, because these laws are based on the motion of the particles. They're not based on our perception of that motion, based on what we feel hot or cold. They're based on the motion of the particles, so we have to go to the scale that measures that. Oops. Okay, so here's the Charles law example. So again, notice the temperatures are in Celsius, so you're going to have to change that. But other than that, you just plug in and go like any old algebra problem. Okay, so if you're watching the video, I apparently left out a slide. So when we go over this in class, we'll talk about Gay-Lussac's law, Gay-Lussac's law, however you want to say it. It is another gas law, and I can't write on here, I'm still figuring out my computer, but it is a formula that involves pressure and temperature. They are directly proportional, which means one will go up, the other goes up. You'll still use Kelvin for your temperature, so be aware of that. And like I said, I'll get it all kind of fixed when we go through and talk about it together in class. Okay, so here is actually our fourth gas law. It's the combined gas law. So it looks at all of the variables, the pressure, the volume, at an absolute temperature, which is going to be the Kelvin temperature. And so again, we work them kind of the same way. We'll be solving for one variable, but using all three conditions. Okay, sorry. Are we going? All right, so here is the combined gas law problem. So note, you've got more information, but you'll have everything that you need in terms of the variables, and then have one thing to solve for. Okay, so now to the end, and this is really the whole point of our study of fluids, is fluid mechanics. So can we use this some of these properties of fluids to do work for us. And hydraulics is a big part of fluid mechanics, and it is the magnification of a small input force on a confined liquid to produce a much larger output force. This is based on Pascal's principle. Remember, squeezing the lotion bottle will the lotion, which is the fluid, will transmit pressure everywhere, and it will push. So Pascal's principle says that I can raise a car if I have a hydraulic press, or a hydraulic lift. And so here is our little picture, which I think is such a good explanation. You have over here the input. So this is where somebody pushes the button, and a little lever kind of pushes down, and you have a little, some kind of little mechanism that is just lowering down onto that water in that little skinny tube. That pressure starts to push, the fluid starts to push on all the other fluid around it. That pressure is magnified in that small space, and so it continues to be magnified as you move all this way over here. Whoops. And then you get here, and it has nowhere else to go but up. And when it pushes with much greater force, and it is enough to lift that car. We have lots of different things that work on hydraulics, like the thing at the top of doors, that kind of keeps it open from like slamming shut. I'm sure there's a word for it. That's based on hydraulics. A syringe is really kind of like a hydraulic, and kind of reverse. But anyway, so this is kind of one of the big uses. We can kind of harness that power and make it move heavy things for us. Okay, and then the other principle is Bernoulli's principle. Daniel Bernoulli, 17th century, he said that a faster flowing fluid has a lower pressure than a slow flowing fluid, which sounds kind of counterintuitive. It seems funny, but it's used to explain explain the lift that is produced by the wing of an airplane, because of the way the shape of the wing kind of causes a change in pressure. Where the air is moving over the wing faster or slower will lower the pressure, which means things get pushed up, which is the lift that we talk about. It's why when you put your finger over the edge of a water hose, it seems to come out faster, even though there's there's a smaller amount of water coming out, or a smaller space for the water to come out. So anyway, so all of this is based on fluids. Pipelines run based on Bernoulli's principle and have different configurations and different little narrow little passages like the picture. That helps you kind of maintain the pressure. That's where they check the pressure. So anyway, so fluids, big deal, good to know about. All right, let me turn it off, maybe.